All right, so to continue our discussion about conservation of energy, um, and so that we can line up and have that test prior to holidays, because nobody wants to, right? Like the Monday or Tuesday we come back, that would be Grinch-like of myself. We need to move on here. So motion in the Earth's gravitational field, or in other words, potential energy. Now, potential energy doesn't necessarily have to be gravitational, although that will be our focus. Potential energy is also in the form of chemical energy. Um, I guess chemical, electrical are somewhat related there as well. And an argument can be made that electrons outside their shell is a type of gravity as well, kind of thing too. So, anyways, we're going to focus on gravitational field. So, vertical work and potential energy. Work done lifting a mass, vertical distance d or h, both letters are used. Obviously d for distance, h for height. Is stored inside the body as increased potential energy. And for some, who knows why reason, the letter U is used for potential energy. Most students would say, Mr. Bennett, shouldn't it just be the letter E with a P? Because you have EK for kinetic energy, and I have a hard time disagreeing with you. So if you want to go ahead and use EP, you go right ahead. Every year I get to this point and say, yeah, I really should change. Get rid of all those U's and change them. And then, of course, the next lesson comes up and I don't do it. So increased gravitational potential energy, UG, right? Gravitational, or just plain old U. Remember W equals FD? Since F is equal and opposite to weight force, which is mg, and D and H are synonymous, then W equals FD simply becomes U equals mgh. And that's probably not the world's best written out version of a derivation. If you want to see it a different way, right? Any work done is a change in gravitational potential energy. So however you want to show that, basically what it boils down to is U equals mgh. Okay? It's the energy of position. When it's released, it instantly turns to kinetic energy, right? Not a particularly challenging concept. Okay, here's where it maybe gets a little bit sort of interesting, I suppose. Let's say you've got a 5 kilogram cannonball or what have you, and it's in the top of an 8 meter high cliff. What is the gravitational potential energy? mgh, 5 times 9.8 times 8, or 392 joules. What is the kinetic energy? 0. Why is it 0? Not moving. Sitting there on the ledge enjoying the sunshine. Total energy, ET, not to be confused with the lovable 80s movie, ET. Still have it on VHS at home. ET, total energy, is equal to kinetic energy plus potential energy, or 0 plus 392, and the total energy is 392 joules. Why did I do this step over here? I'm going to show the total energy throughout, because obviously the ball is going to fall here, right? I'm going to push it off. I'm going to show you that the total energy remains the same throughout because of that law of conservation of energy. Okay, so what I'm going to do now is I'm going to change the slide. This stuff's going to disappear, and this stuff's going to slide up, and I'm just going to make some room. Please don't rewrite that first row again, right? And people do that. Say, Mr. Bad, we already just wrote that. Don't write it again. Okay? So, again, I'm not sure why I did this. They could be gone. Okay, so that's what we just wrote, right? Okay, so now it's at 3 meters of height. Or is it? And here's where I always get confused. I confuse myself. Oh yeah, it is. It's at a height of 3. Right. Right? So it's now at a height of 3. Mass remains the same. 9.8 remains the same. height is now 3. We now have 147 joules of potential energy. Where did the potential energy go? It was converted into kinetic energy. Let's determine the kinetic energy. How do we determine the kinetic energy? We got to know the speed. Here's where it all starts fitting together. It's like that point in the puzzle where you finally start seeing what it's supposed to look like, right? And you know you're going to get it. This is it. Vf squared equals Vi squared plus 2AD, an old gem from back in September. Initial velocity is 0, 2 times 9.8 times 5. You get a final velocity of 9.9. Well, whoop-de-doo.
We got to 5 meters.
Ah, very good. This 5 right here is because it fell 5 meters. And I guess technically we should have a negative 9.8 there and a negative there. And technically the final velocity is negative because it's down, but it's not going to come out negative because it's a square root thing, right? So you got to sort of be careful. Let's determine the kinetic energy. We found out yesterday that it's equal to mv squared over 2. Mass of 5, 9.9 is our velocity, square it divided by 2, 245 joules. Some number that really doesn't mean anything. Vf squared equals Vf squared, right? So you have to take the square root. Vf squared? Pardon me? Oh, well, I guess. Fair enough. The magic happens. Oh, there was a good question.
To find the EK, couldn't we have just taken the 392 original potential energy? Oh, okay.
Absolutely, my friend. Joey's absolutely right. What he's saying is, couldn't we have just taken 392 minus 147 and got 245? And he's absolutely right. But I wanted to show you, first of all, that when you do it this way, that the total energy does remain the same. So I don't really want you doing this until you've seen that it's actually true. So from here on in, feel free to go right ahead and do this, because that shows me you understand conservation of energy. The total energy here is 245 kinetic and 147 of potential. And as it falls, the kinetic energy increases and the potential energy decreases. Let me throw a monkey wrench into things. How do you explain terminal velocity then? Like, let's say instead of 8 meters, it was 8,000 meters. Well, terminal velocity happens when you can't, the air resistance is equal to the weight force, and you don't accelerate anymore, and you just move at a constant speed, right? But clearly, as you're falling, your what is dropping? Potential energy. So if it can't be converted to kinetic energy, heat. Which is why they got to put those special tiles on the space shuttle, right, so it doesn't burn up. Okay. Heat. Absolutely.
Still,
Pardon me?
still like.
Yeah, so the total energy is the same. If you could somehow measure that heat loss, then you could. Okay, good. When it's at the bottom, and I don't think this is particularly, well, I guess. This just shows conservation energy. You don't need to write this down. Delta U, change in potential energy, is 147 minus 392 minus 245, right? It lost 245 joules of potential energy. UF, final potential energy. UI, initial potential energy. It lost 245 joules of potential energy, and interestingly enough, gained 245 joules of kinetic energy. That's a long way of saying what Joey said at the start. Couldn't we just subtract? So, sort of in summary here, total energy is the same at all times. There is conservation of energy. And as the object moves, the changes in potential and kinetic energy are equal and opposite. Now, I hate to say this, because it just shows you what... You've probably heard me talk about being at Canada's Wonderland and figuring out stuff in my head, right? Maybe you've forgotten that because you blocked it out. But anyways, there's this big ride at Canada's Wonderland. There's these two poles, kind of like this. And then there's a wire, right? And they strap you in right here. And then there's another one, there's another pole like back. Yeah, I don't know if it's called drop, but there's another pole like back here kind of thing, right? With another wire, and then it pulls you back, just like, you know, you pull a kid back on a swing, right? And then the person that's hanging there has the release thing, and they can release the swing, and then they go screaming down at the bottom, right? So I was standing there thinking, I wonder how fast they're going at the bottom. Because that's what I do. So I estimated the height that they were up, right? How high up in the air they were. Figured out, okay, well, average person weighs about this, times 10 instead of 9.8, because I can do that in my head, multiplied by height. All of that potential energy is converted to kinetic energy, so then I'm going back to EK equals mv squared over 2 in my head, come up with a value, multiplied by 3.6. So, ooh, that's pretty fast. So then, of course, I went online at the hotel, and it said right on there, yeah, riders will reach up to speeds of, and I was within about like 10 kilometers an hour. I was the only one excited about it. But that's what I did. Thank you.
Right.
Hey? Are you kidding me? There's no way I would ride that. It was, in fact, I realized after, Dan, that I was standing like, there's like a fence here. And I was standing like here, kind of like directly underneath the person as they went screaming over my head. And I remember thinking, this is probably not a good spot to stand because, like, you know, if something happens, bodily fluid kind of thing. I don't want to be here. Okay. One of my favorite cartoon characters, Rocky the Flying Squirrel. He's 1 kilogram, which makes him easy to multiply. He's initially 10 meters up in a tree, and he jumps down to the ground. Find the total energy at the start, and find his velocity after he's fallen 6 meters, using energy. What's his total energy at the start? Well, it's all what? All potential. U equals mgh, 1 kilogram, times 9.8 times 10, 98 joules of potential energy. How do we find his velocity after he's fallen 6 meters? Well, let's do it the energy way. If he's fallen 6 meters, then that means he's 4 meters from the ground, right? So let's find his potential energy at that height. 1 times 9.8 times 4. $39.2 joules. That means total energy is potential plus kinetic. 98, 39.2 plus EK. So the kinetic is 98 minus 39.2. I always get to this point here. Oh, having problems today. Is that the long way? Probably, right? What could we have done? You don't need to write this. We could have just done this, right? Distance he fell was 6, right? hoping it's the same. Much easier that way. But this shows conservation of energy. So I might say to you on the test, I might say, show me that you understand conservation of energy by doing it this way. That's all. Okay? But I want you to realize that, see how what I meant about it all coming together kind of thing? Everything fits. Want to try this one? You should for sure be able to do A and B and C. Yeah, you can probably do them all. Give it a whirl when you do my testing. Did you get that for the first two questions? Hopefully everyone got 2,500. Did everyone get 2,500? Yeah? Give me a nod. Give me something, you guys. Yeah? Emily, yeah? 2,500? Yeah? Okay. Dan, why you got your earbud in, Dan? 2,500. Why can I do this? Because when you launch it up, right, all of this kinetic energy at the bottom becomes potential right at the top, right? At the very peak there, when it's not moving at all of that kinetic energy is transferred. So you can make this step here. It's a little easier. What about kinetic energy when it's risen halfway off the ground? Well, to do that, you need B, right? So you would have to take 127.6 divided by 2. I don't have that. 63.8. And we want to know the kinetic energy. So how am I going to do that? What's the best way? Can I combine it all in one sort of giant step? Could I do something like this? Total energy must be 2,500. We are asked to find the kinetic energy, just this. I think we can do this. Is it any great surprise that it's basically half? Should be no big surprise, right? Halfway up, it's got half kinetic energy, half potential energy. What was the last question? Well, it's risen 100. Okay, so the last one here, when it's risen 100 meters off the ground. Basically, you do exactly this, just what? Put 100 in there for each, and instead of leaving it as kinetic, you have to actually convert it when you're done, right? So same steps. Let's do it in one big step like this. I got 23.2. Did you get that? All good? You guys are so quiet. Pipe down, Anders. Okay, well, let's have a look at the last one here. How about you guys, again, give it a whirl, and I'll show it to you in about 5 minutes. Okay, so how do we do this? Well, I think these have all been the same, really, haven't they? Like, there's not a whole lot else I can throw at you. Total energy, 1350. Potential, or height of rise, 45.9. Velocity just as it lands on the ledge, that's that sort of monster two-step stuff, 28.3. Is that all good? No? I meant sort of like understanding-wise. No? Okay, I'll pause. All right, well, let's have a look and see. Everyone's good with A and B then, finding the total energy and the height? So we've got ET equals EK plus U. The total energy altogether is 1350. EK is made up of mv squared over 2, and potential energy is made up of mgh. So 1350, mass is 3, v squared over 2 plus 3 times 9.8 times 5, giving us a potential energy. So it kind of looks like this, right? Like it's got 1350 joules there at the bottom, and then it lands on this ledge. So based on that height, the potential energy here is 147. So it's still got a lot of kinetic energy, which makes sense, right? Like it goes up high like this, and it comes streaming down and lands on that ledge. So 1350 equals 1.5, that's 3 divided by 2, v squared, plus 147. The 147 goes to the other side, so it's subtract. And then you got to divide by 1.5 and take the square root. And you end up with 28.3 meters per second. So it's still moving quite fast. Well, of course it would be. It's not still moving, it's moving quite fast because this height, it went up 45.9 meters and this ledge is only 5 meters high. So this is not really for scale, is it? That make sense? Sally, yeah?
On the way down?
Yeah, look. Well, no, but the 1.5, I just divide by 1.5, right? When the positive 1.5 goes to divide, it doesn't become negative.
Or that step, or that what you actually did. Oh, wait, you just moved the 147.
Yeah, I just moved the 147. I guess what I really did was I moved the I moved everything and then changed the signs around, didn't I? Yeah. Now, I had someone over here said, shouldn't it be negative 28.3? And the answer is yes, it should. But that's not going to come out of the formula because of that squared thing, right? So it's a situation where you would have to actually manually put that in, if need be. No, I'm not going to write that. Okay? Yes? No? These guys are scaring me. All right, there's a problem package there. We'll do springs on Monday. Aiming for that Thursday test.